Imagine an ant. Not the tiny creature you can brush from your arm, but an ant the size of a man, its armored body clicking, its multifaceted eyes staring into yours with an alien intelligence. Imagine a dragonfly, not hovering. To see it, we must travel back in time, deep into a past so alien it's almost unrecognizable. We are going to the Carboniferous period 300 million years ago. Forget the world you know. The air itself is different here. It's thick, heavy, and wet, shimmering with an energy you can't quite place. The reason? The atmosphere is saturated with oxygen. Not the 21% we breathe today, but a staggering 35%. This oxygen-drenched world is a planetary-scale greenhouse, covered in continent-spanning swamps. But the trees are not trees as we know them. They are colossal, 50-meter-tall club mosses and giant horsetails. And in this supercharged air, this hothouse of evolutionary potential, the true rulers of the world are not vertebrates. They are the arthropods, the creatures that, in our time, have been relegated to the cracks in the pavement. Here they are giants. Look, that creature skittering through the damp, rotting forest floor, weaving between ferns the size of buses. It's not a lizard. It's Arthropleura, a millipede. But it is a millipede that is 2.5 meters long, 8.5 feet. It is an armored freight train of segmented chitin, as long as a car, the largest land invertebrate that has ever lived. It has no known predators. It is a titan of the leaf litter. And in the air above, that is not a bird. It is Meganeura, an ancestor of the dragonfly. But its wingspan stretches 75 centimeters, 2.5 feet, the size of a modern golden eagle. It is an apex predator of the air, its serrated legs snatching smaller creatures from the sky with terrifying efficiency. Even the creeping things are nightmares. A scorpion, Pulmonoscorpius, hunts in the gloom. In our world, its descendants are small dangers. Here it is 70 centimeters long, the size of a small dog, its stinger poised and lethal. This was a real world. These fossils are not theories. They are facts, pulled from the rock. This was the age of giant insects. They were the masters of their domain. And then, they vanished. As the oxygen levels fell, their kingdom crumbled. Their descendants, the dragonflies and millipedes and scorpions of our world, are ghosts. They are tiny, pale shadows of the titans that came before. This raises the single most important question of this story. The giants existed. We know it. We have the proof. So what exactly is stopping them from coming back? What biological law holds the insect world captive, and what would it take to break it? Look at your own hand. Feel the bones inside. Take a deep breath. Feel your chest expand, your lungs fill. In these simple, unconscious actions, you are demonstrating exactly why you are a giant, and why the ant on the floor is not. The animal kingdom you belong to, the vertebrates, and the one insects belong to, the arthropods, were locked in an evolutionary war for dominance that began over 500 million years ago. And your lineage won, hands down. The arthropods, for all their success in numbers, are trapped. They live inside a biological prison of their own design, a prison defined by two fundamental, inescapable laws. The first law, and the most important, is the law of breathing. An insect does not have lungs. It does not have a nose or a mouth for breathing. It does not have blood that carries oxygen. The entire massive six-legged kingdom is built on a respiratory system that is, by our standards, shockingly primitive. An insect breathes through a series of tiny holes along the side of its body called spiracles. These holes open into a network of microscopic, branching tubes called tracheae. These tubes pipe oxygen directly from the air to the creature's cells, a process that relies entirely on passive diffusion. Think of it this way. You have a superhighway system with hemoglobin in your blood acting as millions of delivery trucks, actively picking up oxygen from your lungs and racing it to every cell. An insect has a tiny, winding network of one-lane country roads, and the oxygen has to, essentially, walk to its destination. This system is ingenious at a small scale. It's light, simple, and requires no energy. But it is also a biological dead end. It is governed by a ruthless physical constraint known as the square cube law. This law is the single greatest tyrant in all of biology, and it is why we have number 10-foot-tall ants. The law states that as an object gets bigger, its volume, its internal mass, increases faster than its surface area. Let's apply this. Imagine an ant. Now magically scale it up to be twice as long. Its surface area, which includes the openings of its tracheal tubes for breathing, increases by a factor of 4. But its volume, the number of cells needing that oxygen to live, has increased by a factor of 8. The ant's demand for oxygen has octupled, while its ability to supply it has only quadrupled. It suffocates. Now scale that ant up to the size of a dog. Its body is a vast, dense metropolis of cells, miles from the nearest road. It would be dead in minutes, asphyxiated by its own bulk. The only reason the giants of the Carboniferous could exist is that the 35% oxygen-rich air was so potent, it could force its way down those tiny tubes deep enough to power their larger bodies. In our 21% oxygen world, that is impossible. To be big, you need lungs. Insects don't have them. The second law of the prison is the exoskeleton. An insect wears its skeleton on the outside. This suit of armor, made of a tough material called chitin, is a miracle of engineering at a small scale. It provides protection from predators, prevents water loss, and acts as a rigid frame for its muscles to pull against. But once again, the square cube law turns this triumph into a catastrophe. That same ant, scaled up to the size of a car, now faces a new gravitational nightmare. Its exoskeleton's weight has increased exponentially. Its legs, which were pillars of strength when it was small, would be too heavy to lift. The armor itself would be so thick and ponderous it would barely be able to move. Worse still, if it did somehow manage to move, the rigid, hollow tubes of its legs would snap like uncooked spaghetti under the immense stress. The only reason a large crab, which also has an exoskeleton, can exist is because it lives in water, where buoyancy does 99% of the work of holding it up. On land, against the full, crushing force of gravity, an exoskeleton is a tomb. But the true horror of the exoskeleton, the single event that makes large-scale insect life an impossibility, is the molt. An external skeleton cannot grow. In order to get bigger, the creature must shed its skeleton. This process is called ecdysis. For a small caterpillar, this is a dangerous afternoon. It splits its old skin, crawls out, and hides under a leaf for a few hours while its new, soft skin hardens. Now imagine our car-sized ant. It must break out of its old, massive shell. It emerges not as a giant, armored warrior, but as a 10-ton jello mold. Its body is a soft, pulsating bag of flesh, completely unable to support its own weight. It would collapse instantly into a helpless, quivering puddle, a feast for any predator, or simply a victim of gravity, its own internal organs crushed by its own mass. It would be helpless not for hours, but for days, maybe weeks, as its new, colossal skeleton tried to harden. This is not a viable survival strategy. It is a biological checkmate. To be big, you need an internal skeleton that grows with you. Insects don't have one. Every prison, no matter how perfect, has a key. And the key to this one, the one that could shatter the laws that bind the insect world, is the sky itself. But to turn a beetle into a behemoth, you don't just need a key. You need a cataclysm. You need to reset the entire planet. For the tiny creatures to become Earth's giants, two fundamental, world-breaking events would have to occur. One is the catalyst. The other is the opportunity. The catalyst, as we learned from the Carboniferous, is oxygen. The 21% oxygen level of our modern world is the on switch for our own biology, but it is the off switch for giant insects. To break the chains of their tracheal system, the atmosphere itself would have to change. We would need a new, massive, and sustained spike in global oxygen. We're talking about a return to the 30% or 35% levels of that ancient past. How could this even happen? It would require a profound shift in the planet's biosphere. The original Carboniferous spike was caused by the explosive, planet-wide success of the first great forests. These new plants were so efficient at photosynthesis they pumped out astronomical amounts of oxygen. And, crucially, when they died, they fell into swamps where the normal bacteria and fungi that cause decay hadn't yet evolved to break them down. They were simply buried, their carbon locked away. That buried carbon became the coal and oil we burn today. All that locked away carbon meant the oxygen it was once bonded to as CO2 was left free in the atmosphere. To recreate this, we would need a new, global photosynthetic revolution. Perhaps a genetically engineered species of algae, released into the oceans, blooms uncontrollably, choking the seas in a planet-wide green tide, drinking in CO2 and breathing out O2 on a scale we can barely comprehend. Or perhaps, in a post-human world, new forms of plant life evolve, with a hyper-efficient form of photosynthesis, turning the continents into a single, dense, oxygen-producing jungle. This process would take millions of years, but slowly, painfully, the atmospheric concentration of oxygen would climb. The air would become thick and heavy again. Fires would burn with explosive, terrifying speed. And in the leaf litter, the tiny tracheal tubes of insects would begin to work more efficiently than they had in 300 million years. The first lock on their prison would begin to rust. But this alone is not enough. High oxygen in the Carboniferous produced a 2.5-meter millipede, yes. But it was still just a big, slow, clumsy millipede. It wasn't a complex, fast, intelligent giant. Why? Because the jobs for large, complex animal were already taken. Back then, the first amphibians and reptiles were already on land, already experimenting with the body plan that would eventually lead to us. And today, the competition is infinitely more severe. This brings us to the second, far more violent requirement: the opportunity. You cannot have new giants until you have gotten rid of the old ones. You need a great vacancy. You need a mass extinction. We're not talking about a small one. We are talking about an event so devastating it wipes the slate clean. Think of the asteroid that hit 66 million years ago, ending the 160 million year reign of the dinosaurs. That event created the single greatest job opening in the history of life. The niches of large land herbivore and large land predator were suddenly, violently vacant. And who filled them? The creatures that survived. The small, the humble, the generalists. The tiny, shrew-like mammals that had been scurrying in the dinosaurs' shadows for 100 million years. With their competition vaporized, they exploded in a riot of evolutionary creativity, radiating out to become the whales, the elephants, the lions, and us. For the insects to have their chance, they would need their own KPG extinction. An event so specific and so brutal that it doesn't just kill the large animals, it kills all large vertebrates. Mammals, birds, reptiles, gone. Perhaps a designer plague, a hyperlethal virus that only targets vertebrate biochemistry. Perhaps a massive gamma ray burst from a nearby supernova, sterilizing the surface of the continents. Whatever the cause, the result must be the same: a world emptied of all its large competitors. A world where the largest animal left alive is no bigger than a lizard, and where the most numerous, diverse, and widespread creatures are the arthropods. Only then, in a high-oxygen world, with all their ancient enemies dead, would the real evolutionary journey begin. The prison door is open. The guards are gone. Now the insects must evolve or die. The new world is broken. The air is thick, strange, and rich with fuel. The cities of humanity are silent, crumbling ruins being swallowed by a hyper-aggressive, oxygen-fueled jungle. The giants are dead. The age of mammals and birds is over. And in the damp, quiet earth, a new dynasty is stirring. The survivors, the beetles, the spiders, the ants, the mantises, are thriving in this new atmosphere. The high oxygen has solved their most immediate problem. It floods their simple bodies, allowing them to grow larger generation by generation. We see beetles the size of dinner plates, mantises as long as a man's arm. But this is just the first step. They are still trapped. They are still clumsy, heavy-bodied creatures, bound by their ancestral chains. To become true giants, to become the new masters of the planet, they must do something that evolution has almost never done. They must tear up their 500-million-year-old blueprint and start again. The first problem to solve, the great gravitational enemy, is the exoskeleton. It is too heavy. It is too weak at scale. It is a death sentence every time the creature must molt. It must go. But how? Evolution doesn't make enormous, sudden leaps. It makes tiny, incremental changes. The process would be agonizingly slow, taking tens of millions of years. Perhaps it begins with internal reinforcing. Small ridges of chitin might begin to grow inward from the exoskeleton, like the struts inside an airplane wing, to provide better support. In a high-oxygen world, where metabolism is fast, this process could accelerate. Generation after generation, the selective pressure for better support would favor creatures with larger internal ridges and thinner outer shells. The outer shell, no longer the primary support structure, would become leathery, flexible, more like a reptile's skin. Over millions of years, these internal ridges would become more complex, fusing together. They would form a scaffold. First, a simple series of rods and plates, and then, eventually, a true, articulated internal skeleton. This new skeleton might not even be made of chitin. Evolution is a tinkerer. It uses what's available. Perhaps these new creatures would evolve a way to bind calcium into their internal scaffold, creating a new form of bone, strong, light, and, most importantly, living. It could grow with the animal. The nightmare of molting would be over forever. This creature, this descendant of a beetle, would now have an internal skeleton. It would have solved the problem of gravity. It would no longer be an arthropod in any meaningful sense. It would be something new, a convergent solution, a new vertebrate for a new world. But an internal skeleton is useless if the creature can't power it. A strong frame is nothing without an engine. And that brings us back to the second, greater prison, the lungs. The passive, dead-end tracheal system, even in a high-oxygen world, will never be enough to power a 50-ton, active, warm-blooded giant. To make that leap, the new giants must invent the lung. This is, perhaps, the single most difficult challenge. Where would it even come from? The answer might lie with the spiders. Spiders and scorpions, unlike insects, have a different, slightly more advanced respiratory system. The book lung. It's a small, internal chamber with a series of thin, leaf-like plates, like the pages in a book, that allow oxygen to diffuse into their blood. It is still passive, but it is internal and contained. This is a starting point, under the relentless pressure of an evolutionary arms race, where the creature that can run faster, hunt longer, and think quicker survives. These simple book lungs would be under immense pressure to become more efficient. The pages would become thinner, more numerous. The creatures would evolve muscles to pump air in and out of the chamber, no longer relying on simple diffusion. This is the birth of active breathing. As the creatures grow larger, these simple pumps would become more complex. The lungs would fold in on themselves, branching into smaller and smaller airways to maximize surface area, just as our own alveoli do. And to transport all this new, abundant oxygen, the old, inefficient, clear hemolymph of insects won't cut it. They would need a true circulatory system. Their simple tube-like heart would have to evolve, folding in on itself to become a powerful, multi-chambered muscle, a true pump. And their blood would need an oxygen-binding protein. Perhaps they would perfect the copper-based hemocyanin of their spider or crustacean ancestors, turning their blood a deep, rich blue. Or perhaps, in a stunning echo of our own evolution, they would stumble upon the magic of iron, evolving their own independent form of hemoglobin, their blood turning a familiar, shocking red. This new creature, 100 million years after the fall of man, would not look like a giant ant. It would be a completely new phylum of life. It would be a hexapod, a six-limbed creature with an internal, calcified skeleton. It would be warm-blooded, its metabolism roaring thanks to a high-efficiency, four-chambered heart and a pair of complex, branching lungs. It would be descended from an insect, but it would have converged on the exact same solutions that made mammals and dinosaurs the masters of their own worlds. It would be the new apex of biology. And now it is ready to inherit the Earth. Welcome to the new world. It is 150 million years in our future. The air is thick and sweet with 32% oxygen. The sun shines down on a planet you would not recognize. The continents have drifted. Great mountain ranges have risen and fallen. But the most profound change is the life. The age of mammals is a forgotten layer in the rock. The age of birds is a distant memory. This is the new Carboniferous. This is the age of Arthropoda. The planet is ruled not by fur and feather, but by armor, antenna, and mandible. Look to the plains. Those are not forests of oak and pine. They are vast, towering jungles of silica-rich superplants, evolved to defend themselves against the new masters of the world. And browsing the tops of these 200-foot-tall glass trees are the new herbivores. They are the Titan beetles. Descended from the humble, armored Coleoptera, they are 6-legged, 40-ton behemoths. Their front wings, the elytra that once covered their ancestors' flying wings, have fused into a single, massive, articulated shield of armor that protects their backs. Their 6 powerful, pillar-like legs carry them in great, thundering herds across the plains. Their mandibles, once designed for nipping at leaves, have evolved into a complex set of interlocking, grinding plates, capable of pulverizing the glass-hard plants they feed on. Their senses are alien. They communicate not with sounds, but with complex, chemical pheromones, wafting great clouds of intent and warning across the herd. And where there is prey, there is a predator. Stalking the herd from the shadows of the jungle is a mantis lord. Descended from the praying mantis, it has long since sacrificed flight for size and speed. It is 30 feet long, a bipedal hunter that uses its 4 rear limbs for a shockingly fast, galloping stride, its body held horizontal to the ground. Its 2 raptorial forelimbs, the praying claws of its ancestor, are now 6-foot-long serrated scythes, powered by muscles of terrifying strength. It is warm-blooded, its new lungs and powerful heart giving it the stamina to run down its prey. It does not hunt by smell, but by sight. Its colossal, compound eyes, each a foot across, are the most advanced visual organs this planet has ever produced, able to see in spectra we can't even imagine. It strikes with chilling, mathematical precision, a silent, green-armored nightmare. In the skies above, the Dragon Kings rule. They are the descendants of dragonflies, but they are no longer simple gliders. They are warm-blooded, their powerful new lungs fueling massive, internal flight muscles. With 50-foot wingspans, they are the new eagles, the new apex predators of the air. They hunt the giant, flying descendants of moths, but they will also stoop from the sun to attack a young mantis lord. A clash of titans that rains blood and chitin onto the plains below. The world is a web of new, terrifying food chains. The rivers are choked with multi-legged, armor-plated crustacean descendants, the river scorpions, that ambush anything that comes to drink. And then there is the strangest, most terrifying evolution of all, the social insects. In the great equatorial deserts we find cities. They are not made of stone and steel. They are termite mounds. But these mounds are half a mile high, built with a chemically bonded cement as hard as granite. Inside, 1 billion individuals, each specialized for a single task, serve a new kind of consciousness. The queen, a vast, immobile, pulsating creature at the heart of the city, is no longer just an egg layer. Her colossal brain, a fusion of millions of ancestral ganglia, is a biological supercomputer. She is a true, sentient intelligence, but not an individual one. She is a collective, a planet-spanning consciousness. She wages war, plans agriculture, and directs the evolution of her own colony. It is a new form of life, a new definition of person. This is the world that could be. A world of 6-legged vertebrates, of biological supercomputers, of a planet reborn in the image of the insect. It is a beautiful, terrifying, and spectacular vision. Planet completely reinvented. A world where the most humble creatures beneath our feet rise up to become titans, to build empires, to develop consciousness. It's an incredible story. So, when does it happen? When do the real rulers of Earth finally take their throne? Here is the cold, hard, biological truth. They won't. The story we have just told is a fascinating exercise in biological speculation, but it is, in all likelihood, just a story. The reign of giant insects is biologically possible, but it is so profoundly improbable as to be functionally impossible. The hurdles are simply too high, and the competition is too good. First, let's consider the evolutionary leaps we described in Act 4. The transition from an exoskeleton to an endoskeleton. The invention of a high-efficiency lung from a passive trachea or a simple book lung. The evolution of a four-chambered heart and iron-based hemoglobin. These are not just leaps. They are chasms. They are fundamental rewrites of a body plan 500 million years old. Evolution does not work with a goal in mind. It cannot decide to invent a lung because it would be useful. It can only work with tiny, random mutations. The number of sequential, beneficial mutations required to turn a trachea into a lung is so astronomically high that it may have only happened once in the history of life on this planet. To ask the insects to do it all over again, and to do it better than the creatures that are already here, is asking a bicycle to evolve into a jetliner, one random screw at a time. But the real, final, unassailable barrier to the age of insects is not their own biology. It's ours. The most important fact in this entire story is the competition. The scenario we built in Act 3 required a great vacancy, a mass extinction that wipes out the mammals and birds, giving the insects a clean slate. But this is a loaded die. Mass extinctions are not clean, and the creatures that are best adapted to survive them are mammals and birds. Let's run that experiment again. An asteroid hits tomorrow. The world is plunged into darkness and cold. The megafauna, the elephants, the lions, us are gone. Who survives? The insects? Yes. But who else? The rat, hiding in its burrow, eating anything. Seeds, roots, garbage, other insects. The crow, an intelligent, adaptable generalist that can solve complex problems and eat literally anything. The cockroach, the lizard, the survivors of any apocalypse are the small generalists. And when the dust settles and the sun comes out, who is best positioned to fill the empty giant niches? The beetle, who must now spend 50 million years inventing a lung and an internal skeleton. Or the rat, who already has a lung, an internal skeleton, warm blood, a four-chambered heart, and a highly advanced brain. The rat is not at the starting line of the evolutionary race. It's at the finish line, lacing up its running shoes, while the beetle is still trying to figure out how to build a foot. Within a few million years, the world would not be filled with titan beetles. It would be filled with giant, 10-ton rodents, carnivorous supercrows, and massive, predatory rat kings. The age of mammals would simply begin again. Our tiny, shrew-like ancestors proved this 66 million years ago. They were poised, ready, and evolutionarily light years ahead of every other phylum. Their descendants still are. The tiny creatures that scurry at our feet are not pretenders to the throne. They are not future giants biding their time. They are the masters of a different kingdom, the world of the small. In that world, they are the undisputed kings, and their success in numbers and diversity shames our own. The giant insects of the Carboniferous were not a preview of the future. They were a miracle, a fleeting, spectacular, and unrepeatable accident of a time when the air was rich and the land was empty. It was a window of opportunity that slammed shut 300 million years ago, and it will never open again. The creatures of our world have chosen their paths. And for the arthropods, that path is to be small, to be numerous, and to be masters of their own tiny, perfect universe.